Okay, looks like we're live. So hello, everyone. Welcome to another talk in our webinar series. This webinar is also being streamed live on YouTube. You can find the link on our website or access it on our YouTube channel, Linea MCTI. Today, we have the honor of having Dr. Pierluca Carenza, a postdoctoral researcher from the University of Stockholm and the Oscar Klein Center. Dr. Carenza is an expert in the astrophysical signature of axions and other feebly interacting particles. His research is mostly focused on the impact that axions that are emitted by stars will have on the star's evolution. Most recently, he's been working on blue balls, a likely candidate for dark matter particles. He's also this year's winner of the Giuliano Preparazza Prize. Congratulations for the award. Dr. Carenza, thank you so much for being so kind and having accepted to give us a webinar talk today on such an exciting topic. The floor.
Okay, thank you. Thank you for the introduction. Your momentary frozen. So this talk I will show you some application of the axion phenomenology, so the impact of axions, these hypothetical particles, in astrophysics. So let's start with, since this is mostly the interest of this talk is about astrophysics and signature of axions, I will not talk about the particle motivation, the motivation behind the axion, the first introduction of this hypothetical particle, which is connected with the strong CP problem to solve this problem, the standard model. But in any case, it's only to say that axions are interesting and motivated particles beyond the standard model, and the axion is a boson, typically with a very unconstrained range for masses and interactions that we'll see later with standard model particles. And axions are very relevant in astrophysical and cosmological context because they will have a strong impact on the stellar evolution, and also they could compose dark matter. So it's extremely interesting for this particle that was originally introduced to solve a problem related with the strong interactions to be also a candidate for dark matter. And not only in string theory and in other beyond the standard model complete theories, axion particles, axion-like particles, or particles like similar to axions with similar properties, appear in a very natural way, like in string theory. They appear very often after some compactification of the extra dimensions. So now we'll see what is precisely an axion, but for us there are many reasons to think about this particle and its role in astrophysics. So an axion is a boson, and then for our purpose, we only need to know that the axion interacts with the standard model particles. There are many different interactions. The most important for phenomenology is this interaction with this vertex with two photons. So we have this Feynman diagram, which follows by this Lagrangian here. And then we can use this Feynman diagram to create all the possible processes that we want involving axions and photons. So for example, the axion can decay into photons, or if one of these two lines is an external line, like an external magnetic field or electric field, so the axion can oscillate, it's called, into a photon. So there is this mixing that we'll see later in more detail. And another important property is the interaction of axion with the fermions in general. So the fermion can be a nucleon, neutron, proton, or electron. And in general, these are the particles, the interaction with the important fermions for our phenomenology. This interaction is given by these Lagrangians, where there is a derivative coupling. And we have a vertex like this. So processes involving fermion can emit an axion. This is why axions are produced in stars very often. Not only there is a particular property of axion, that their coupling, that we'll see very often in the slides, this coupling with photons is called Ga gamma, or the one with fermion is called Ga fermion. These coupling are naturally very small because they are proportional to the inverse of this new physics energy scale, this FA, which is connected with new physics, so it's well above the TV scale. And then this coupling becomes very small in a natural way. So this is only the first basic idea of axions. And then we'll see how to use this idea to have an impact in astrophysics. So for example, in the first application, we'll see how axions and axion-like particles affect the evolution of low-mass stars. First of all, let's see how to describe a low-mass star, or a star in general during its evolution. This is the famous Hertzsprung-Russell diagram, a diagram in which you see on the x-axis there is the surface temperature of the star and the luminosity on the y-axis. So every single point is a point that is representing a single star with these two different properties. So stars like the Sun in the main sequence, they populate this region, here, the Hertzsprung-Russell diagram. And then during the evolution, they start to go up in the diagram because become more bright. And at some point, so what we are interested now in this application to horizontal branch stars, which are stars populating this horizontal part of the Hertzsprung-Russell diagram, in which there is a core composed, because the stars like with an hydrogen core that is burned to produce energy. At some point, the hydrogen in the center, in the core, is finishes and is converted into helium, which can be burnt also in later stages to create energy and to contrast gravitational collapse. So the star that we are interested in now is the horizontal branch star, this phase here. In this type of stars, axions can be emitted because using the interactions before, we can have an oscillation of a photon interacting with ion, with the electrostatic field of an ion, and converting into an axion. So these are photons from the thermal bath inside the star that are converting into axions, and this process is called Primakov conversion. There is another process which is also relevant in this case, which is simply obtained by the first one by replacing this external field with another real photon. So there are two photons that are merging into a single axion, and this process is typically very efficient for heavier axions, and we'll see what heavier means. And now, so axions can be produced in these HB stars, especially in the core, which is the dense and hot region of the star, and they are emitted and they subtract energy from the star. So subtracting energy means that the evolution of the star becomes faster because there is more need of burning more and more fuel to sustain the exotic energy loss given by axion and also the gravitational collapse. So it means that this phase in which axions are produced, which is the HP horizontal branch phase, typically becomes shorter with introduction of axions. Now, how to measure this quantity? This should be typically proportional to the number of stars in the Hertzsprung-Russell diagram that we saw before in this horizontal branch compared to the number of red giant star, which is a stage in which axions are not emitted. So in this ratio, we simplify, let's say, all the constant quantities, and what's left is only this time, which is this ratio, so it should be proportional to the duration of this phase, in which one phase is affected by axion and the other is not affected. This quantity is measured, and so if this quantity is compatible also after the introduction of axions with observation, it means that an axion is still possible with that parameters, in that parameter range. And this is what we did in this paper, doing the numerical evolution of these HB stars, including axions. with a very large range of masses from below. So this is the coupling with photons, and this is the axion mass, which is largely unconstrained. For axion masses below 10 keV, this line is all the same because we are in a range in which the mass is much lower than the temperature of the star, which is around 10 keV in the core. And in this range, so axions act like massless particles. This bound is valid here on the left. And then as the mass increases, the bound becomes weaker because there is less production of axions because of the Boltzmann suppression. Clearly, heavier particles are produced with a smaller efficiency inside the star. And then this region, which is the purple region here, excluded so by this constraint, becomes smaller for higher axion masses, in which higher here 100 keV, in which both the processes, Primakov and interstick that we discussed before, are relevant. So in this plane, I also show other constraints on axion-like particles. For example, there are other constraints coming from, and we will discuss also this one later, from supernovae or from laboratory searches. Now, at the moment, it's only important to see that in this plot, we have an interplay between different astrophysical probes and also laboratory searches, which is interesting to give the idea of the interdisciplinary level of the axion. And this small region here, unconstrained, is called cosmological triangle, only because this is a region which is excluded by cosmological consideration. So there is also this other level of cosmology which is involved in the discussion. Now let's see other applications, like with the supernovae, axions emitted from supernova. So a supernova is the final stage of a massive star. A star, like I said before, burns elements starting from hydrogen in the core to produce heavier and heavier elements that accumulate in the core, forming this onion-like shell structure in which heavier elements go into the center, and in the outer shells there are lighter elements. At some point, the core is composed by, if the mass of the star is large enough, more than 8 solar masses, the core becomes composed only by iron, and the iron cannot be burnt anymore because it's the most stable nucleus. It means that there is no energy to contrast the gravitational collapse, and the outer part of the star collapses on the core, shrinking the core to very high densities, and which this core which will produce the future neutron star. And then, so since the matter is very dense, the external envelope bounces back, producing the so-called supernova explosion, which releases a lot of energy. And in this extreme environment, the density is huge. The core of the supernova, the density is about the nuclear density, so it's a very large density. The temperature is very large. If Googling this, I understand that this is the hottest place in the universe for Google, but in the supernova core, the temperature is like 1,000 times hotter than this place here. And not only, there are also magnetic fields which can be quite intense, like 10 to the 15 Gauss, which is the strongest magnetic field that we can find in nature. So the supernova core is really an extreme environment, and that's why we need these extreme conditions to produce axions, first of all, because they are weakly interacting. Not only, another particle that is copriously produced in a supernova, which is also weakly interacting, are neutrinos. And neutrinos, we know neutrinos, so we can model neutrinos in supernova simulations. And we know that their properties can trace back a lot, can give a lot of information on the internal structure of the supernova explosion. And this is only a plot to show how neutrino luminosities evolve in time in different stages of the stellar evolution, of the supernova evolution. We would be interested only in the last stage, in which which is a featureless, let's say, phase in which the energy of the supernova is slowly released in neutrinos, and it cools down in the future neutron star. So in this phase, which is called the cooling phase, we can see strong deviations from the standard behavior because of the axion production. But how to quantify this impact of axions on neutrinos? Well, we detected only one supernova, neutrinos coming from one supernova, the galactic supernova 1987A, and the few number, this small sample of events detected by these three different detectors. This represents the number of events collected after the time of the explosion of the supernova. And so neutrinos interacts with these Cherenkov detectors with protons inside to produce positrons. And this is the energy of the positron detected. So this is to give an idea of what we know. These are the only events that we know for a galactic supernova. But these few events tell us that 10 to the 53 ergs of energy are emitted in form of neutrinos, which have an average energy of 15 MeV, and the burst is 10 seconds long, 10 seconds. So we know these few key things about the neutrino emission from a star, and we'll use this, our knowledge, to constrain axion properties. But how to do this? And there is a simple idea behind, which is called the energy loss argument, presented by Raufeld a few years ago. So the idea is that if in the star there are axions and they are emitted by the supernova, so their emission is stealing energy from the core of the star. But this energy is also the same energy that also neutrinos similarly steal when leaving. So at some point we can see an impact on the stellar evolution if these exotic losses, because of axion, this luminosity, is equal or bigger than the neutrino luminosity that we know from the explosion of the supernova 1978 to be equal to this quantity. So this is the idea, this is the constraint that we want to use to exclude some parameters of the axion. Okay, so this is a bit more in detail what happens in general. This is for axion, but can be applied to other feebly interacting particles. Okay, this is the luminosity of the particle as a function of its coupling. When the coupling is very small, so clearly the luminosity is also very small, it's much smaller than the neutrino luminosity, and there is no impact of axions on the supernova evolution. At some point, there is an increase, and the star starts to feel the presence of axion, and so the neutrino burst is shortened because most of the energy is stolen by axions. And at this point, so we have a coupling, which we can exclude from this point on, because here the luminosity is only bigger, it's incompatible with the observation. But what happens? What happens that when the coupling becomes very, very large, axions are not only produced and escape freely, but they interact again inside the star. And in interacting again, axions are absorbed by the material inside the star and re-emitted continuously, a bit like neutrinos when the star is very dense. And so the luminosity goes down. In this going down, at some point, the luminosity, exotic luminosity, becomes again smaller than the neutrino one. So at this point, the duration of the neutrino burst is not affected anymore. Therefore, we exclude only a finite range of couplings because of this criterion. Okay, so in practice, axions are produced inside supernova by this process, which is the nucleon-Bremsstrahlung, in which two nucleons interact by exchanging, for example, a pion. This is the simplest picture that we can have in mind. And one of these nucleons emits an axion. So axions are produced in this way, and because of the very high density of the nuclear matter, this process is efficient. Another process which is relevant was recognized mostly. It was known years before, but it was recognized in this paper recently, is this pion conversion, in which a pion, a pi minus, which is present in the supernova core, even if it's only a few percent, 1%, is absorbed by a proton, and then an axion is emitted in the final stage. So this is another process which is quite different from the previous one, but in any case, we produce axions in the supernova core. And this is an idea of the spectra that we have from the Bremsstrahlung. You see this spectrum, which is peaked around thermal energies, which is 3 times the internal temperature, so 90 MeV, and the harder pion conversion, this process called pion conversion spectrum, which is harder because the pion mass is converted into kinetic energy for an axion. And so we see a different shape. In any case, these two fluxes can be used to calculate the luminosity of axions, and we require that this luminosity is smaller than the neutrino one, obtaining this constraint in green here in the plane, where we have basically the coupling with the fermion, so 1 over a phase proportional to this quantity, and the axion mass. So this is the constraint from the supernova. And in this case, we see that, again, we are excluding a very large region of the parameter space because this is wide in mass. We can go to very large masses because of the high temperature of the supernova. And there are other astrophysical constraints with which this one is complementary. Okay. Another application in supernova is for axion-like particle of axions that interact with the photons instead of fermions, we saw before. So the interaction are the same that we saw before for in an HB star, precisely the same. It's only a different magnitude of the luminosity, more luminosity emitted. So these are the two processes, the Primakov and the inverse decay. And in the same way, one can calculate the luminosity and require that this luminosity is smaller than the neutrino one, obtaining the purple bound here in supernova. As you see, there are an upper and a lower limit for the coupling because of the trapping that at some point prevents the axion and efficient axion production. So this is the constraint, which is in this region that we already discussed, complementary with other searches. Okay, and these are indirect searches to find a constraint, but we can also, in principle, ask if axions can help the supernova explosion, because we know that if axions that they decay inside the star, they decay into photons, and so it means that axions are produced at some point and then they decay again, redepositing the energy. And if it happens in the proper region of the star, it could help to revitalize the shock, the explosion. And this is happening in this is a zoom of the previous bound. This is the region excluded. And here is a part delimited by the red line in which the axion energy, deposited energy, could be enough to revitalize the explosion. So axions are not only useful, supernovae are not only useful to exclude axions, but also could give a hint on the axion, or the presence of axion, or in any case, it's an interesting complementary discussion. Okay, and we can also try to find at some point, instead of indirect signatures coming from this cooling idea, direct signatures. One example is the diffuse supernova axion background. So at the moment, we know that axions are emitted inside the star because of the interaction with nucleons or electrons, which they do a similar interactions like nucleons. This is called also Bremsstrahlung, or photons by photon interaction. In any case, we have a production mechanism inside the star, and then axions go around in the universe, and many things can happen. For example, an axion could convert, interacting in a magnetic field, could convert into a photon, or if the axion is massive, it could efficiently decay in a couple of photons that we detect as gamma rays, or depending on the energy, very often gamma rays. Or also axions could decay in E+, E- couples because of their interactions with electrons. So there are many different things that can happen. The phenomenology is very large. And now we start with the idea. Axions are reproduced inside the star and they escape their light, and so they efficiently convert into photons. So what are the signatures that we have from this process? This is an example of the diffuse supernova Flux, which means that we are considering that a single supernova emits axions, but also all the supernovae in the history of the universe emitted axions. Therefore, there is a relic, let's say, relic flux of axion around in the universe, and depending on their interaction with fermions or with photons, there are different magnitudes for this flux, as you see in this plot. Typically, the energy of this flux is higher compared to the diffuse neutrino flux that we think to exist and should exist. Because axions are produced inside the star when the star is hotter, and so their energy is higher. Okay, this idea, so we have this flux coming from all the past supernova explosions, which could convert, if axions are light enough, could convert in the magnetic field of the galaxy, of our galaxy. The magnetic field of our galaxy has a particular shape, and so there is, it's not constant, there is a particular morphology, therefore, of the conversion of axions into photons. This is, for example, a scheme up of this probability of conversions of axions into photons, and you see the probability is higher towards the center, where the magnetic field is more intense, and then it decreases strongly with the radius, and in the upper and lower part you see a particular shape given by these off-plane components of the magnetic field in our galaxy. So we expect some, if axions convert into photons in this magnetic field, we expect some morphology, particular morphology, because of the magnetic field. Therefore, we can use axions are produced from in this figure. You see that the energy is in the gamma ray regime, because this is the same energy that the axion is also the same energy of the final photon after the conversion. So we are in the gamma ray regime. In the gamma ray regime, there is the experiment Fermilat, looking at gamma rays coming from around the sky. And this is a scheme up of the signal detected by Fermilat. In this signal, so probably we could try to find a particular morphology related to the shape of our galactic magnetic field. And the predicted axion signal is something like this one, which is very different from the background before. Therefore, we can do an analysis, an accurate analysis, to compare this signal with background, excluding this region of the parameter space on the top of this shaded area, which represents the uncertainty on this constraint. So all this region is excluded by this comparison. This is a different region compared to the one that we discussed before, that was a bit higher masses. Now the mass is very small, and many axion models are justified for these very small masses. As you see in this range, there are also other searches, as always, like astrophysical searches for spectral modulation of X-ray from galaxy clusters, which are the strongest constraints at the moment, because this excludes very small Ga gamma. But it works only for a few masses, for a small range of masses. In our larger range, there is this constraint. There are also others coming from laboratory experiments or other constraints that could, in any case, have a loophole. So it's always important to look at different signatures of the axion. And even if the region is here already excluded, but this bound could be improved in the next years with more data coming from different experiments and repeating the analysis. So this could improve. Another idea is, okay, we have this background that could, of axions that could decay into E plus, E minus, and they give different signatures because this decay into E plus, E minus is very particular. What happens once that the axion travels around and decays in E plus, E minus, we have extra positrons in our, could be in the galaxy or could be also from other sources, we'll see. For example, in our galaxies, if there are extra positrons, it happens that positrons scatter with electrons and they lose energy in 10 to the 3, 10 to the 6 years, depending on their original energy. And they lose energy. At some point, they go at rest or very close to the rest, and then they annihilate with an electron of the background. This annihilation happens in different waves by different channels. Could be a very unlikely direct annihilation, like E plus E minus going into gamma gamma, which gives this monochromatic line for the photon. This is the origin of the famous 511 keV line, which is detected by many gamma ray experiments. Or the other process is the formation of a bound state, the positronium, which has two different possible combination of spins. And because of the two different combinations, in one case, there is a decay in 2 photons, and in the other, to preserve the angular momentum, in 3 photons. So the one in 3 photons is not extremely useful for our searches because it gives a broad signal, not a line like the decay into gamma gamma into 2 photons. So we have a single line. We are interested in this in this channel, which gives a single line. All the photons are there, and since every process connected with axion, like the decay into E plus E minus, is rare, it's better that everything is going into a single line to amplify our signal. So we look at the impact of axions on this 511 keV line. And our question is it possible to explain this 511 keV line, which is partially unexplained, with the decay of axion-like particles and with an extra injection of positrons in our galaxy? So so this flux is measured with this shape at 511 keV. We have clearly a flux coming from the center of the galaxy or from other particular regions which are identified, and this partially unexplained. This flux has a particular morphology, so it's connected with the shape of the galaxy. It's focused towards galactic center. And so our idea is, what if there is a supernova emitting axions and they decay into E plus E minus? This, we expect this signal to follow the morphology of supernovae, which also in the history of the universe, of the galaxy, there were many supernova explosions, and they were all following this distribution, which is peaked. The supernova distribution is peaked toward the center of the galaxy. So it's a very similar shape. And this is the main motivation to see if axions could explain this particular process. So this is, for example, a schema in a small region of the sky in which we have this flux of 511 keV photons coming from the axion decay. And so this is tracing precisely the supernova distribution in the galaxy, because axions with very large coupling like this, they decay very soon, very close to the parent supernova, and then they trace back the supernova evolution, the supernova distribution. And then so there are positrons that are trapped, in any case, in very small regions because of the magnetic field of the galaxy. And when they annihilate, we see this flux coming. And this is a continuous flux because the process has a time scale, a very long time scale. What happens if the coupling is smaller? Axions can travel far and they decay very far from the supernova, so the distribution appears to be smeared. So we can use these two different morphologies to compare with data. So these are data coming from this experiment SPI as a function of the latitude. This is the SPI data. And the two cases of the two couplings with the small and big coupling for axions decaying close to the supernovas, we have a more peak to the supernovas. So we have more peak distribution, and far, so we have a broader distribution. There is a good agreement in this direction as function of the latitude. However, as function of the longitude, there is a strong disagreement. So there is no way that this mechanism can explain the 511 keV line. Anyway, this mechanism could be used to constrain axions, because we don't observe this particular feature. Therefore, we put some constraints that I summarize here in this plot, like in the red part, on the coupling, which is a very large constraint because it spans many orders of magnitude for the coupling with electrons, and some order of magnitude for the coupling with nucleons, which is responsible for the production of axions. Otherwise, something else that can happen is that axions are they are producing their own galaxy, which is not the Milky Way, and they escape because of their very long lifetime, and they decay into plus and minus outside of the galaxy. At this point, it happens so there are positrons around that annihilate in a larger time, because the density of electrons around out of the galaxy is smaller. The scale is gigayears, and we calculate this flux, which is also redshifted because photons come from different redshift. This has some contribution from different redshift at every energy. And the flux, the predicted flux, is this black line, which can be, it's not more a single line, so it should be compared with different data coming from these experiments, for example. And this comparison gives us another constraint for very small coupling with electrons. So it's an interesting region of the parameter space because of the other searches failed to probe this very small coupling with electrons. And this is an idea of the power of these astrophysical searches to study axions, because, for example, in this case, we see how many orders of magnitude we can span, and these are also motivated. These are range, an important range, which is motivated by other scenarios in which the coupling with electrons arise at loop levels, for example. So it's a very interesting scenario. Okay, so in conclusion, we understand that axion and axion-like particles are motivated for other reasons, mostly because of solving problems of the standard model, and they play a major role in astrophysics and cosmology also, in the case that axions find some experiments. So it could be also good to look at the astrophysical consequences of this other messenger. And there are some open questions. For example, there are interesting open questions on how the energy transfer works in star, because as we discussed for the supernova, axions can be produced and then decay again inside the star, transferring energy in a different way compared to the standard channels, which are mediated by the standard model particles. Otherwise, there are other questions that are partially addressed in some works, other questions that are open. For example, what is the role of Alps coupled with electrons in supernovae, which is particularly relevant when this coupling with electron represents a coupling arising at loop level also. And, or more, there are interesting studies about the Alp photon conversions in magnetic field that are not regular as the one in the galaxy, but they are turbulent, and so we have different particular signatures of axions in this context. Okay, so thank you for your attention.
Thank you, Dr. Carenza, for the very interesting talk. We now have time for questions from the audience. Okay, I'll go first then. I actually have a question regarding your use of feebly and weakly. You seem to use them interchangeably. Is that how it's usually done, or is there like a difference between them?
Okay, in general, so weakly interacting particles, which refers more to particles really interacting because of weak interactions or with that order of cross sections. For feebly, we refer to particles that interact weakly in the common sense of the word, so their interaction is very small, even smaller, typically, if you look at the numbers, than weakly interacting particles. So it's not order of the weak interactions cross-section is much, much smaller. And there are different signatures which are not because of typically feebly interacting particles have different signatures like this one, not compared to their scattering and so involving their cross-section. So that's why they're called feebly without omitting this role of weakly.
So axions are both?
Weakly in the common sense, because the interaction is very weak, and feebly in the, let's say, in the scientific sense, if we want.
Okay, thank you. I have another, since no one. Okay, I guess I'll ask another question. Sorry. So, is the hierarchy between nucleon and electron coupling theoretically motivated?
Okay. Yes, in this case here. Okay, so typically.
Sorry, this might be trivial.
I was muted. Yeah. Okay. No, so typically, as we said, the coupling of electrons and protons, they're proportional to 1 over this new energy scale. And the model-dependent couplings are in classical normal models, standard models, common models, they're order 1. So it's not so motivated a huge hierarchy between these two couplings, but there are many other models in which the 3-level coupling of electrons, for example, is suppressed compared to, so at that point we have is completely 0, and so we have to invoke a 1-loop level coupling, which can be larger, than 3-level 1, but still much smaller than GAP, so the other one. So that's why there is some hierarchy here. And in any case, this constraint, for example, is probing both a range in which the two couplings are of similar orders here, and also one in which there is some hierarchy. So it's partially motivated, yeah.
Thank you. Let's see if we have more questions. I'll look on the YouTube. Just a second. No, okay. Okay, so I have another question, if that's okay. Right, so are there other consequences of the very hard spectrum for pion conversion?
Okay, so let's take the slide. Oh, so this is the, okay. The slide, you mean this one, comparing Bremsstrahlung and pion conversion fluxes. So the pion conversion flux is much harder than the other one and of any thermal process. And at the beginning, we thought that this signature could be used to detect axions directly interacting again by the same process, but in the opposite way in Cherenkov detections on the Earth. But then after calculating the cross-section of this process, it's only slightly smaller than what's needed for the future next generation experiments. So probably this is an idea that could be used in the next future. And so not for the next generation experiments, but a bit more in the future. Otherwise, at the moment, I don't have any other phenomenological consequences of this difference. But it's still interesting because it's a very hard and particular spectrum. Very unusual.
Okay, thank you, Pierluca. We still have time for questions from the audience, other people. And it can be very basic and trivial questions also. Since most people aren't used to listening to axioms, listening to talks about axioms in general. Okay, so if there are no more questions, we'll wrap this up. The presentation will be available on our website and on Linea's YouTube channel. I want to thank everyone for attending, and a special thanks to Dr. Carenza. Everyone have a great day, stay safe, and I hope to see you all again in the next webinar.
Bye-bye. See you.